So, to start off with our discussion here of relative motion or relativity, okay, then what we're going to do is we're going to start off with an idea here that light is moving at constant speed. So let's imagine that we start off with a box and we have a laser emitter and a mirror at the top of the box, and so light goes to the top of the box and comes back down here. I'm going to call that distance right there D. Okay. And so if that distance is D, then the time that it takes light to get top to bottom, I'm going to call this T naught. The time it takes to get to the top of the bottom is obviously going to be 2D over C. So that's the time it takes to get from top to bottom. So if you're standing here measuring that happen, the light gets from the top back down here. Okay, now. So now let's say that our spacecraft or our box is moving with some velocity v, and light goes top to bottom in there. What's going to happen? Well, if you're standing here watching it, what you notice is that we got our box, light starts going up, but the box is going to be over here by the time the light reaches the top. So light really took that path. Okay, and then the light bounces back, but now the box is over here in the time it takes the light to get there. So that means really light traveled that path right there. Okay, so if the box is not moving, then we know that the time here is going to be 2D over C, time to get there and back. What about in this case? How long does it take to do this? Okay, so obviously it's the time in this case is going to be 2L over C. So all we got to do is figure out what is L. Well, if we call that distance there X, and that's D, then we know that L is going to be square root of X squared plus D squared. Okay. So what is X? Well, X is just going to be equal to the velocity times the time. Well, the time is actually 1/2 of the total time. Okay. And so because that's just L, that's only 1/2 the distance right there. So if I plug this in here to L, and so I plug this into there, and I plug that into back over here, then we see that the time is going to be 2 over C times the square root of 1/2 VT squared plus D squared. Okay, now D, well, what is D squared? Or what is D? Well, D is just that distance right there. So that D is going to be 1/2 times C T naught. So let me put that in here too. So T is 2 over C square root of 1/2 V T squared plus 1/2 C T naught squared. Okay. Now, why did I do that? Well, I did that primarily so that I could take this and relate the time that one person measures to what the time the other person measures. Doing a little algebra, we see that all that cancels out right there. Okay, and the 1/2 squared factors out, take the square root, and so the other thing I can do is I can divide out a C, and so T is going to be 1 over C squared times actually what I'm going to do is I'm going to square both sides. Okay, so T squared equals 1 over C squared times V squared t squared plus c squared t naught squared. So factoring all that out, okay. And so then I can cross multiply the c squared there, okay, or I could actually I could divide that through. So t squared equals v over c squared times t squared plus t naught squared. Move this to the other side of the equation. So t squared times 1 minus v over c squared equals t naught squared. Okay. Or t is 1 over the square root of 1 minus v over c squared times t naught. Okay. Now, t naught is the time that a person measured here is the time that someone measured in a stationary setting. T is what the moving observer or the stationary observer measures if the whole thing is moving. So in other words, if this is stationary and light goes up and down, you measure t naught. If it's moving, the time it takes to do that is t. All right, now, here's the problem. Einstein says what we call the principle of equivalence. If this is moving at constant velocity, then every measurement you make has to work the same way. So the person inside here measures the same time whether it's moving or not. Whereas a person on the outside measuring it measures a different time. So they measure a different time. So you have two different observers watching the same event, and they measure different times. So t, this is for the stationary observer moving, 1 divided by 1 minus v over c squared. T naught is the time measured by the moving person. So you have two different things that are happening here. Time measured by a stationary observer and time measured by a moving observer. And they're different. The difference is this factor right here. We sometimes call that the gamma factor. Okay, so we define gamma to be equal to 1 over square root minus v over c squared. Okay, now what does this mean? The bigger v is, the bigger that v is, the smaller the denominator is, and so the bigger the gamma, meaning this time is much longer than that time. In other words, for a stationary observer, you measure longer time than for the moving observer. Likewise, for the moving observer, you measure less time. Okay, we can do algebra here and find that t naught is square root 1 minus v over c squared times t. This is what the moving observer measures. That's what the stationary observer measures. So this is going to be a smaller number. So as v gets very big, it becomes smaller. So notice if v is approaching the speed of light, then the stuff under the square root gets close to 0, and so less and less time. So in other words, this is what they call the twin paradox, that have twins here, and they're both the same age. One gets in a spacecraft, flies it near the speed of light, comes back. They're not the same age anymore. The one that was stayed stationary may have had 20 years pass, but the one that was moving may have had only 5 years pass. So they're the same age, but when they get back together, one's 20 years older and the other is 5 years older. Okay, now this sounds really weird, but it's actually been experimentally verified that moving objects, time runs slower in. So they did this by taking an atomic clock and putting it in an aircraft that flew around the world. And so it's going at high velocity. They compared it to another atomic clock that stayed at the airport. when they landed, the one that stayed at the airport was ahead of the one that was moving. Not by much, but by a little bit. The faster you go, the bigger the effect. This is actually a big enough effect that if it's not compensated for, then your GPS will not read the correct position because the time will be off compared with the time that's happening in the satellites, which are orbiting the Earth at much higher velocity. Now, Lorentz factor, gamma is called the Lorentz factor. The Lorentz factor notice what happens when V equals C. It goes to infinity. Or in other words, back to here, I said that T times square root 1 minus V over C squared equals T naught. Okay, so if V equals C, that means T naught is 0. Now, T naught is how much time passes for the moving observer. That means if something is moving at the speed of light, no time passes. In other words, if you were going the speed of light, you would simultaneously be leaving where you left, arriving where you start, or rather, you'll be leaving where you start, arriving where you end up, and simultaneously be everywhere in between. Okay, no time passes. You are simultaneously everywhere. A beam of light shining from the Andromeda galaxy 2.5 million light years away. It takes 2.5 million years to get here. As far as the light is concerned, it arrives the same instant that it leaves. It's also at every spot in between. Time does not pass. Because time does not pass, acceleration is 0. You cannot accelerate if you don't have a change in time. Therefore, if you're going the speed of light, you cannot speed up or slow down. You cannot change. This means that the speed of light is an absolute speed limit. You cannot, if you speed up and you were to reach the speed of light, you could never speed up or slow down again. You'd go that speed forever and ever, never changing, because time will not pass for you. Therefore, you cannot change. So if something is not going the speed of light, it cannot actually reach the speed of light because time goes slower and slower and slower. And so at some point, it would take longer than the age of the universe to change. And so you would never change. So you can never reach the speed of light if you're going slower than the speed of light. Likewise, you cannot, if you go the speed of light, you cannot go faster than the speed of light. Some people say, well, what about going faster than the speed of light? Well, here's the problem with that. Okay. What happens if V is bigger than C? That's not defined. If you're going faster than the speed of light, you're not part of the universe. Somehow you are orthogonal to the entire universe, orthogonal to all dimensions of space. Okay, so you're no longer a part of the universe. That's what it would mean to go faster than the speed of light. It does not mean going backwards in time. It just simply means that you are not even part of the universe, and once you're out of the universe, you cannot get back into the universe. So that means the speed of light is this absolute speed limit. Okay, this is the result of this time dilation.